Picking up where we left off on our Chapter 7 lecture notes. So when we left, we were finishing up with the main ideas of the Bohr model. Okay, and so continuing on, we go with the idea that electrons are like college students. The lowest energy is preferred. And that's, kind of the way it is for most people, not just college students. College students are simply better at showing that preference. But anyways, so the energy of an orbital is dictated by the distance from the nucleus of a particular orbital. By the distance from the nucleus. All right, so for example, n equals 3 versus n equals 2 versus n equals 1. N equals 3 is farthest away from the nucleus, okay, and has the highest energy. Right, so the amount of energy is directly related to the n value. Right, so n equals 3 is okay. N equals 2 is better because it's closer and lower in energy. N equals 1 is best, okay, because it has the lowest energy. Right, and we can calculate the energy of a particular orbital. We have a nice simple equation for that. So E of an orbital is negative RH over n squared. Okay, and RH is called the Rydberg constant. And has a value of 2.179 times 10 to the negative 18 joules. Okay, and again, just to calm your minds, I do not expect students to memorize constants. Okay, if I ask you to do this type of problem on a test, I will give you the value of the Rydberg constant. Okay, so for n equals 1, energy of that orbital is negative RH over 1 squared. Okay, we just take the value for n, plug it into the equation, and we can calculate that energy. So negative 2.179 times 10 to the negative 18 joules over 1 just equals negative 2.179 times 10 to the negative 18 joules. Okay, and that is the energy for n equals 1. Now, we've been talking about this idea of electrons transitioning between energy levels, and they can only do so in discrete energies. Okay, so to calculate the energy for a transition, so the change in energy, that's a delta. My triangles are not very good. The energy for a transition in a Bohr atom is, delta is still E final minus E initial. So delta E, E final minus E initial. So I can use that same equation, and I get negative RH over n squared final minus negative RH over n squared initial. Okay, so you can absolutely solve this equation like this, okay? But a simpler version is to just distribute through those negative signs and move things around a little bit, and we get a sort of more streamlined version of the equation. 1 over n initial squared minus 1 over n final squared. Okay, so when we distribute through those negative signs, it swaps the places of the initial and final. That's all it does. Okay, but it's still the same delta final minus initial. We're just rearranging to get rid of all of those negative signs. Okay, so to calculate the energy of a transition, all we really have to do is plug in the value for the Rydberg constant and the value for the n values, the values for n. So for example, delta E for transition from n equals 5 to n equals 2, right? Here's my 5 is my initial, 2 is my final. Right, so I'm going to take and plug in those values into the change in energy equation. So delta E equals 2.179 times 10 to the negative 18 joules, 1 over 5 squared minus 1 over 2 squared. Okay, so 1 over 25 minus 1 over 4. That quantity by itself should give me a negative value. Right, and then I multiply by the Rydberg constant, and I should get a negative energy. So that comes out to be negative 4.576 times 10 to the negative 19 joules. Right, so delta E is negative. Right, so it loses energy. Right, that means that it gets more stable. Remembering that because electrons like to be at lowest possible energy, so when they have the least amount of energy or less energy, they are more stable than when they're at higher energy. Now that amount of energy leaves as a photon. Right, so this is emitting a photon, or we call this emission. Right, so when an electron goes from high to low, that energy has to leave somehow, and it leaves in the form of a photon. Now we can also cause an electron to go from low to high, but in order for that to happen, it has to absorb some energy, okay, usually in the form of light. Right, so we can calculate that wavelength of that light. And that's one of the main purposes of starting this chapter, talking about how to do calculations with light and energy. Okay, so we have our equation E equals hc over lambda. So if I rearrange that equation to solve for lambda, I get lambda equals hc over E. Right, and this is our energy of emission that we just calculated. Right, so the wavelength of that emission, 6.626 times 10 to the minus 34 joules seconds. That's the Planck's constant. Then our speed of light, 3.00 times 10 to the 8 meters per second. All divided by our emission energy, which was 4.576 times 10 to the negative 19 joules. Okay, now you may be wondering why I have not included the negative sign. Because for this type of thing, all I care about is the magnitude of the energy. Okay, in the previous problem, coming up here, this negative sign here is more about telling me which direction the energy is going. Is the energy going out or is the energy going in? Okay, it's not necessarily something that affects the numerical value. Right, so when we calculate our wavelength here, we're not concerned with whether the energy is going out or going in. We just want to know the wavelength. Okay, we already know that it's emission, so we know that the energy is going out. So the magnitude is all that matters to us. And I'm going to convert this wavelength to nanometers. 10 to the 9 nanometers per meter. We'll find that this comes out to be 434 nanometers, or dark blue. Okay, so let's do another one like this. So what is the transition energy? From n equals 3 to n equals 2. Okay, so delta E equals our RH value, the Rydberg constant, 2.179 times 10 to the negative 18 joules. N equals 3 to n equals 2. That makes 3 my initial, 2 my final. So 1 over 2 squared, excuse me, have that backwards, 1 over 3 squared minus 1 over 2 squared should give me a value of negative 3.026 times 10 to the negative 19 joules. Right? The negative sign tells me that it is losing energy. Energy is coming out, so this is emission. Right? It's a lower energy photon emitted, so it's going to be a longer wavelength. So this is going to be more red in color. Okay, so just to come back a quick little step. So how do I know that it's more red in color? So our equation for energy as it relates to wavelength. Okay, so I can interpret this qualitatively. I can look at that and say that as wavelength gets bigger, energy gets smaller. Okay, talking about a number in a denominator, as that denominator gets larger, the value of the fraction gets lower, right? So lower energy must be associated with a longer wavelength. Right, so compared to our previous example, we had an energy of 4.5 to the negative 19. So here we have 3.0 to the negative 19, so that's a lower energy, longer wavelength. So if I'm at darker blue to start with, my wavelength gets longer, I'm going to be creeping towards the red direction of the spectrum. Okay, we're going to go ahead and stop this video here, and we'll pick it up on the next one.